Math 2312, section 1.6, absolute value equations and inequalities. This problem really wouldn't belong in this section because it's not an absolute value inequality, but I do want to show you an example of a different type of inequality to show you that the technique that we've been using is a little bit more universal in the sense that it applies to pretty much all inequalities, not just absolute value inequalities. For this example, we're going to solve a rational inequality, rational meaning the ratio of two polynomials. X squared minus 16 over x minus 2 is greater than or equal to 0. And in this example, I'll also demonstrate why when I originally gave you the second step, it said partition the domain of the function instead of partition the number line. Other than that, it's going to flow just like before. So we're going to start by making this say equals and solving x squared minus 16 over x minus 2 is equal to 0. If we were to solve this, well, it's an equation and it has a fraction, so we should probably multiply both sides by the denominator. You have to be a little careful though when you multiply both sides of an equation by a variable expression like x minus 2. Because multiplying preserves equality, but sometimes it can take false things and make them true if what you're multiplying by is 0. For example, 7 is equal to 10, except it's not. That's false. But if I multiply both sides of it by 0, then it would make it true because now it would say 0 equals 0. As long as you're not multiplying by 0, the truth value of an equation is preserved. Meaning if you have something that's true like 5 is equal to 5 and multiply by 2, it's still true. Or if you have something that's false like 5 equals 3 and multiply both sides by 2, it's still false. Multiplying by a non-zero number preserves an equation's truth value. Multiplying by 0, however, can take something that's not true and make it true. So you have to be careful when you're multiplying by 0. But when you're multiplying by a variable expression, you don't know if it's equal to 0 or not because you don't know what x equals. So technically, anytime you multiply by a variable expression, you have to put this stipulation that what you're multiplying by isn't equal to 0. I know this isn't discussed a lot in lower level lower level math classes, but as you go up the math ladder, it becomes more important to stay cognizant of things like that. That when you multiply both sides of an equation by something, that something shouldn't be 0. So I'm going to write the stipulation over here that x minus 2 can't equal 0, which is the equivalent to saying that x can't equal 2. Now, if you're really paying attention, you already knew this from the original problem. Because x equals 2 would make the denominator 0, and that's a domain violation. So keep in mind, x was never allowed to be 2 in this problem to begin with. It was easier to see at the beginning. But anyway, if we multiply both sides by the denominator, it leaves x squared minus 16 on the left. 0 times anything is 0 on the right. We have a couple of options on how to solve this quadratic equation. An easy one is to add 16 to both sides and then square root both sides. But I mentioned in class more than once that when you square root both sides of an equation, you have to throw in a plus minus to pick up all solutions, and we get x equals plus or minus 4. All right, so those are our solutions to the equation, and we also have this added restriction. Keep that in mind. Now, when you go to partition the number line, you are going to partition it at 4, negative 4. However, this inequality, this function, was never going to allow x to be 2 in the first place. So when I said partition the domain of the function, what I mean was draw the domain of the function and then cut it. This function's domain never, ever, ever had the number 2. So when we go to partition, we can't partition the entire number line because it includes the number that we're not supposed to have. So we're going to partition that thing instead. If we partition it at negative 4 and 4, how many intervals do we have? Hint, it's not 3. It's actually 4. Because before we cut anything, our number line already had a hole in it. So as a piece of string, it was already cut into 2 pieces. and we just cut it 2 more times, which took it to 4 pieces total. Our left interval is negative infinity to negative 4. Now we have to pass judgment on whether or not the negative 4 is included. That boils down to whether or not the inequality allows it to be equal. It does, so we include the negative 4. Same thing between negative 4 and 2, except even though this says greater than or equal to, we still can't include the 2. The 2 is being excluded because it makes the denominator equal to 0. So this 2 does get a parentheses, as does the 2 that starts the next interval. And that next interval ends at 4, which is included, because remember, 4 is what made this equation equal to 0, and it's okay if we're equal to 0. And then on the other side of 4 is 4 to infinity. From this point forward, the rest of it works out just like before. We pick a test value from each interval, and it's worth pointing out that you never pick an end point on the interval. For example, negative 4 is in this first interval. Don't pick it. Why? I already know what negative 4 does. Negative 4, being a solution here, made this equal. I want to see what the rest of the interval does. And again, just to clarify, I use brackets because the inequality said or equal to, but not on the 2 because 2 made the denominator equal to 0. That's what I mean by partition the domain. Watch out for issues that exclude values from your domain. And then the rest of it runs pretty smoothly. We pick a number to the left of negative 4, like negative 5. We pick a number between negative 4 and 2. There's my opportunity to pick 0. I always pick it when the opportunity arises. Between 2 and 4, I can pick 3. I can pick any number like 2.7 or pi, but don't be cute, just pick something easy to work with. And then something greater than 4 like 5. Then we just go back to the original inequality, see which ones make them true or false. I'm only going to work the first one, and then I'll tell you what the results are for the rest of them. If we substitute negative 5 into the original inequality, we get negative 5 squared minus 16 over negative 5 minus 2 is greater than or equal to 0. Without dilly-dallying, the numerator ends up being 9 because it's 25 minus 16. The denominator ends up being negative 7. We're seeing if 9 over negative 7 is greater than or equal to 0, and the answer is no, it is not. The number on the left is a negative fraction, which can't be greater than or equal to 0. This is false. So we would not include this interval. And then we can check the rest of them. For the sake of time, I'm just going to tell you the results. The 0 would make it true. That's actually pretty easy to see because if I put in 0, I get negative 16 divided by negative 2, which is positive 8, which is greater than or equal to 0. We could check 3. 3 will make it false because when you put in 3, I believe you get negative 7. So this comes out to be false, which means we don't want that interval. And then when we pick the x equals 5, we ended up getting 9 over 3, which is positive, so it's good. And again, on a test, you would write out the details because you're showing your work. And if something goes wrong, I can look for partial credit. I do want to say one thing before we answer this. You may have noticed as we do these that the true falses tend to alternate. False, true, false, true. But it's precisely that. They tend to, but they don't always. I have seen problems with back-to-back trues. I can make one up. I've seen problems with back-to-back falses. So you can't make any loose generalizations like, oh, well, every other interval is going to be part of the solution. I just got to find which one to start with. No, you got to check them all individually, which we didn't do, but if we did, that's what they would turn out to be. Trust me. So our answer would be the union of all the intervals that made it true. So it would be bracket negative 4 comma 2, union bracket 4 comma infinity. So this technique does work on other caliber of inequalities. The only thing you have to watch out for are numbers that were never in the domain to begin with, in this case 2, which meant that when we went to partition the number line, the 2 was already excluded because of this denominator. and then we cut it some more at the solutions to the equation that we solved. All right, we'll talk more about inequalities later in the semester, but I just wanted to demonstrate this technique on something that was not an absolute value inequality.